On from yesterday, talking about numerical methods for traveling water waves.
All right, thanks, Dave. So, right, I'm going to talk about computing water waves today with some of the methods that Dave kind of previewed yesterday. And what I'm going to do is do all the things that Dave said. Well, there are these problems that kind of were mysterious to me that I'd like to solve. And I think Dave was a little hard on himself, pretending as though he hadn't solved them. But the answer is he had. And he just wasn't going to tell you about them yet because it's kind of, we're moving through history in the course of this short course. So the next step in history, all these problems with, well, I'm evaluating the free surface above the free surface. Am I allowed to do that? Or evaluating the potential above the free surface? Well, he doesn't do that. He has a better trick that handles that problem, and I'm going to discuss some of that today. And then I'm going to discuss how you might construct waves that are the simplest possible water waves, which I'll call Stokes waves today. And then maybe more complicated water waves, which I'll call Wilton ripples, no matter what they look like. Wilton probably only would have called one of them a ripple, but they're all of the same flavor. So that's what you can look forward to in the next 45 minutes.
Yeah, I was building up the suspense.
Exactly, lots of suspense built yesterday by Dave. So I'll end today actually talking a little bit about how you might show these things are analytic, and I'll leave tons of holes in my discussion so that yet tomorrow Dave can fill them in and return the favor to me.
But there's not going to be any more suspense.
Huh?
There's not going to be any more suspense.
Why not?
Because you're going to give us everything about that deals with the suspense.
Yeah, but it might be wrong.
No, but I'll generate new suspense, and then Dave will do that again on Wednesday, and then maybe we'll leave you hanging. Okay, so there was an outline on the previous slide that you have read, and then I don't have to read it to you. Right, so we're going to talk about traveling water waves with the standard equations. So I have them written here. What's going on. I guess I can say something like we have a flat bottom, potential flow, so there's the water's under, or the fluid's undergoing an irrotational motion, kinematic equation and Bernoulli's equation, so you see there's surface tension here, constant surface tension, and I've already moved to a traveling frame, so instead of time derivatives we have c times eta x and phi x. And what makes these equations hard? Well, they're nonlinear, but nonlinear equations really aren't that hard to solve, except that they exist on unknown fluid domain. So this is kind of the fundamental problem that we'll discuss probably in 13 or 14 talks this month about how do we deal with this unknown domain. Do we do some Dirichlet-Neumann operator, or do we, who knows, tons of different ways. There's really a lot. Boundary integrals, et cetera, et cetera. I'm gonna keep waving my hand and imagine all the different ways I could have listed. So what I'll do in today's talk is I'll exploit that, well, I have non-dimensionalized here, and I've called the wave slope epsilon, and that's suggestive because I'm going to pretend that the wave slope is small. So epsilon is usually what we use for a small number, and I'm going to somehow use that in order to construct traveling water waves. And the first thing I'm going to do...
Is that an actual water? Is it a water wave in your picture?
What do you mean by that?
Is it an actual?
Is it a Wilton ripple? Not quite. It's just a cartoon. It's not too different. I mean, if you squint a couple slides later from now, you might think it looks the same. But this is not the result of a simulation. It's just a free surface I made. So if epsilon is small, then you might try and do a classic technique that you do when you have a problem with a small parameter, and that's what I call an amplitude expansion. So you have some nonlinear problem, so I'm calling f a cartoon for a general nonlinear problem, where x is the unknown I'm trying to find, and epsilon is the measure of amplitude that exists in this problem. And if I can solve the problem when epsilon equals 0, in the water wave problem, epsilon is in front of every nonlinear term, so when epsilon equals 0, it's a linear problem, which I can solve. If I can solve the problem when epsilon equals 0, then I can construct a solution around that. The solution when epsilon equals 0 is here called x naught, by perturbation series expansion in epsilon. So in order to do that, I don't just need to be able to solve the problem when epsilon equals 0. I also need the solution to depend analytically on epsilon, which is something you would need to show. So you could do this and then show it afterwards, or you could show it and then do it after having shown. Either way, what happens as a result of this procedure is, well, you get, instead of one nonlinear problem, you get a sequence of ostensibly linear problems, where you have the linearization around your known solution applying to the next correction, so these xn's, equals some function of the previous xn's. And so if you've already computed x1, x2, x all the way up to xn minus 1, what do you have to do to find xn? You need to invert the linear operator. And if the linear operator was invertible, that would be everything. You just invert this linear operator over and over again. But Well, the linear operator, that was the thing that governed x naught, was the solution to the linear problem. Well, if x naught was a non-trivial solution, that means the linear operator is not invertible. So the first thing I said here, well, I just invert this guy over and over again, you cannot do this. F prime of x naught, the linearization is not invertible, so I can't invert it over and over again. What I could do is invert f prime of x naught against its range. Even if it's not invertible, it's a linear operator, it's going to have some range, and against that range you could think of inverting it. But then what you need to do is enforce somehow that g is within that range. So in addition, so this is, you might call this the Fredholm alternative, or you might call this Lyapunov-Schmidt, depending on where you're from. It's effectively the same idea. From my perspective, Lyapunov-Schmidt is apply the Fredholm alternative over and over and over again. Right, so that means that in order to do this, we need to somehow impose that g is within the range of the linear operator, and we need to somehow, if we're going to do this numerically, we need to compute g in a way that is stable. So somehow g is going to be a function of all these different things, and we don't want, when we add up that function, to get something that is nonsensical. So it might have lots and lots of terms depending on how you map your domain. If you were to do what Stokes would have done, you get garbage. Or at least you may get garbage. So you want to be sure that you're going to get something that you're confident in. So that's essentially the issues are, I want to invert f prime, so I want to make sure g is in the range of this linear operator, and I want to have computed the right g.
One of the things Stokes did was to renormalize gravity in order to get a solvable problem. So don't you have additional free parameters?
Well, you'll see. There are lots of solutions.
Because it's similar to multiple time scale analysis. I mean, if you're talking about solvability or Fredholm alternative. Okay.
Yes. So the answer is yes, and you'll get to see in a couple slides. So first thing I want to do, though, before I do exactly what I just said I'm going to do, I need to deal somehow with this domain. And you could do what Stokes did, which is effectively say, well, I have things happening at a small distance away from 0, so I could Taylor expand everything around 0. And then after doing that, he said, okay, now I Taylor expand and I can actually manipulate these operators and I can find what is the leading order solution to the free surface and what's the next correction, and he even went to the third order correction. And then he stopped. And he recognized that sometimes he wouldn't be able to do this for the Fredholm alternative reason because there would be these ripples. And in that case, he would have to do something else, and he said, well, this is the less important case. And I'll even talk about, well, eventually somebody fixed that case. But it turns out if you do that, what happens? So you Taylor expand around some point, and then everything that's evaluated at that point has a Taylor series that gets replaced with its evaluation at epsilon eta. It now has a Taylor series at z equals 0. And Taylor series have infinite many terms. So instead of having a nonlinearity that was, say, quadratic or some rational function, you get an infinite series of nonlinearities acting at the free surface. And that's the thing I don't want numerically. I don't want an infinite series of nonlinear terms, because then at each perturbation order, the number of terms I have to sum gets bigger. And there's more and more chance for numerical cancellation and terms which I'm adding together to cancel most of the way and give me a really imprecise answer. So this is a thing you know in like a first course in numerical analysis, is that I don't want to subtract two numbers that are close and try and get a much smaller number. I don't want to try and find their difference. So finite difference methods are unstable for this reason. Right? I feel like I should write something on the board. So if I do this, if I do that on a computer and let h go to 0, I don't get the answer that I would like to get when h goes to 0. I get something that scales like the precision of my computer over h. So it actually goes to infinity as h goes to 0 for fixed precision. So this epsilon is not that epsilon. It's like the machine precision. So that doesn't mean you can't use such a formula to find a derivative. It just means you can't compute the derivative as accurately as you want. Right? It actually scales like epsilon over h plus f prime of x. It's effectively what you would get from this formula. So if epsilon is 10 to the minus 16 and you only want to get an answer to 10 to the minus 8, you can do this. But if you want to get an answer to 10 to the minus 16, you can't do this. And it's a similar problem happens if you were to do the Taylor series expansion of the free surface here, is that you can get the answer to reasonable accuracy. In fact, lots of people used these methods in the 80s, like Roberts and colleagues, and they got good answers up to a certain precision. But if they were to increase the precision and repeat the experiment, they wouldn't get better answers, they would get worse answers. And so Dave has a couple papers illustrating this where you plot exactly the same type of plot of the accuracy of your result as a function of the number of orders you keep. And what you find is instead of the error decreasing as you increase the number of orders forever, so this is perturbation order, ultimately the errors start to go back up. So it's not really a convergent series in the number of perturbation orders you kept, unless you increase your precision, and then you can move this minimum down. And you could keep doing that exactly the same way as you could if you were to plot the errors from a finite difference method. So we're going to try and avoid that. And the way that we're going to avoid that is not Taylor series expand, but instead do some other kind of transformation that doesn't give us an infinite number of terms that we have to add together, but only a finite number of terms. So we have less opportunities for this type of cancellation. Yeah, Dave.
Say there's another more subtle problem with carrying out what you propose before the domain transformation that you don't realize until you actually try and do it. And that is that eta, you're going to have some sort of Taylor expansion, and phi, you're going to have some sort of Taylor expansion. But now in those two boundary conditions at the surface, you need to evaluate phi at eta, at epsilon eta. But eta is going to have a Taylor series, so it's worse than the product of two Taylor series.
Oh yeah, when you actually do the perturbation expansion, it's even going to be
It's
a composition of multiple Taylor series.
Analytic functions for which there is not a good formula for what the nth order term is. It's a huge mess. And so actually doing it explicitly is a complete nightmare, and if you code it up, as Marchant and Roberts did, you get an algorithm which has got a terrible computational complexity. And so a huge benefit of the transformation you're about to see is that you get away with this, you get away from that. You never actually have to do that.
Okay, so what might you do instead of Taylor series expand? So I'm going to discuss that on the next couple of slides. So if you Taylor series expand, what you do is you effectively have put a flat boundary in here, where below that boundary you solve Laplace's equation. And so there's nothing to say that I needed to put the boundary at z equals 0, where I solved Laplace's equation before. I could stick a boundary anywhere I want in the middle of this domain and solve Laplace's equation below that. And so that's kind of what I have sketched here. I'll pretend like phi below this boundary has some new letter, call it psi. And certainly if I let psi equal phi, I get back the original problem. But then if I pretend that the value of phi on this line is prescribed as the upper boundary condition for psi, and the lower boundary condition for psi is the original one, then I have an equation that I could solve if you prescribed phi on this interface. I can solve this for psi and get almost the exact same solution I would have gotten for phi everywhere below the free surface. I just get everywhere below a. And so by doing that, I can replace in this equation, so what are the boundary conditions I put here? I put one that phi and psi are the same, but also I want their derivatives to be the same, so that I have continuity of these two, this fake potential and the real potential on this line. And if I do that, so I solve this one, then I know what psi is as a function of phi, and I can take its z derivative, and I'll get a new boundary condition for my problem, which instead of being all the way at the bottom of my domain, is anywhere I want in my domain at some prescribed level a, or minus a here. And doing that gives you kind of a Dirichlet-Neumann type operator just at z equals minus a. So instead of having a domain that I need to solve for from the minus h up to a, I have it now from minus h up to the free surface. I just have it on a smaller domain. And why would I want to do that? Well, my very next step is going to be to map the domain to a strip. So the domain being now from minus a up to epsilon eta. Then I'll map that domain to a strip with the simplest possible transformation that maps it to a strip. So just a rational function in z. So if you plug in z equals minus a, I get minus a minus epsilon a over a plus epsilon a times a. So that goes back to a. And if I plug in z equals epsilon eta, I get 0. So now my domain is mapped to a strip. But this transformation I did wasn't a conformal mapping. It was just some simple mapping that I picked. So that means it doesn't preserve Laplace's equation, nor does it preserve any of the other equations. So everywhere that I used to have nonlinearities and homogeneous, and except for the nonlinearities, homogeneous right-hand sides, now I'll get some extra nonlinear terms. But they won't be so bad. It won't be as bad as if I had done a Taylor series expansion. I won't get an infinite number of nonlinear terms. I'll just have the terms I would have gotten from doing the chain rule in all my derivatives, which the chain rule here just gives me up to cubic terms everywhere. So I had quadratic nonlinear terms, now I have cubic nonlinear terms, but I don't have infinitely many nonlinear terms. I do have an inhomogeneous Laplace's equation, which means I can no longer solve it by hand. So I'm going to have to solve now numerically in the interior of my domain, but how big is my domain? I've added new cost. I was going to numerically solve something on the free surface. Now I have to solve something in the interior domain and the free surface. But how big is my domain? Well, not very big, because I get to pick A. And I get to pick A anywhere away from the free surface. So I can use a really small strip so that numerically I don't have to use so many points. So if I have to use like 16 points, it is 16 times more expensive than a free surface boundary integral method. However, I can do a perturbation series expansion here and get something I can prove converges and is numerically stable. So that's kind of the trade-off we're making here.
And it works in 3D.
And it works in, oh yeah, and fundamentally it works in 3D. Otherwise I should do conformal mapping, because I would get something that's just on the free surface and I would get a homogeneous Laplace's equation. So clearly this doesn't have anything to do with the fact that there's only x here. There could be x and y, and that's still the transformation. Thanks, Dave. All right, so now I want to do what I said I was going to do. I want to solve the linear problem, and I want to expand about that solution for the potential, for the free surface, and for the wave speed. And so when you do that, what will happen, so all the things all the inhomogeneities I introduced, f, j, q, and r, they'll get evaluated at previous orders in terms of, so this f, n, j, n, q, n, etc. There's some formula for them. I'm not going to present it. It's kind of long. But the thing to know is that, at least at first glance, these are known functions of the previous corrections. And so when I want to solve this problem at each order, the unknowns are phi n, eta n, and cn. And I've written this suggestively because I have the linearization over here. That's the thing I want to invert. And then I have some known functions, f, j, q, and r, that I want to make those in the range of the linearization. So somehow I need to impose that they're in the range. And well, I have one more unknown over here that I want to use to impose that I'm within the range of this linear operator. So it's not invertible, but maybe it has one thing in its kernel. And if it does, then I can use one unknown to make it orthogonal to that kernel. Right, and I've said, if you actually went to 0th order, everything over here is gone. So the linear stuff is all on the right side, or on the left side. So what happens at 0th order? Well, a number of things can happen. I don't have to have a one-dimensional kernel. If I do, I'm going to call that a Stokes wave, because those are the waves that Stokes computed, where the leading order solution just looks like a complex exponential and an out-of-phase complex exponential that's the free surface trace of phi, so phi evaluated at y equals 0 or z equals 0. And it has some speed, and at a general value of the bond number and the depth, there's only one frequency that can move at a particular speed. So if we were to plot, I'm going to keep writing on the board. If we were to plot the phase speed, so C here is the phase speed of linear waves, it's also the leading order approximation to the nonlinear speed. If we were to plot that as a function of wave number, it looks like that. I'm not going to say what happens here near x or k equals 0, because it may curve over if we're in finite depth, or it may go to infinity if we're in infinite depth. But if I were to try and find the Stokes wave, what am I effectively doing? I'm saying somewhere on this axis is k equals 1 based on my non-dimensionalization. Maybe it's here. And then I go up and say, here's the speed that my wave is traveling at. And then to decide whether or not I have a Stokes wave like this, or whether I have a more complicated wave, I draw the horizontal line at that speed. So this is here C naught. And I move over and see where does it intersect my phase speed at another point. And that point, well, it's always going to intersect at another point, but I'm trying to find here periodic waves. So if I tell you the period, by telling you here is k equals 1, I go over here and come down to the axis, that's going to be at a general real number. Is that real number an integer? If it is, it fits in my period. If it's not an integer, it doesn't, and then I have a one-dimensional kernel for the periodic problem. So is this k equals m, or k a general real number? So maybe we'll write some bad notation on the board, and then it can be saved for perpetuity. So is it a real number that's not an integer? That's what I mean by that. If it's not an integer, then we have Stokes waves, then we have a one-dimensional kernel, and you can do exactly what I had just said on the previous slide. So there's Stokes looking angry about my presentation of his waves. So yeah, and if you want to go to higher order, what do you have to do? So here's my cartoon from the beginning. You need to invert this linear operator to find the next order correction against the known right-hand side, and you need to impose that this right-hand side is orthogonal to the things in the null space of the adjoint. So what does the Fredholm alternative say? To calculate the speed corrections, I find the things in the null space of the adjoint, call those psi, different psi from before. And then I impose that the things on the right-hand side are orthogonal to psi. So I take an inner product, and well, inner products are linear, so I can break this up over addition, and this gives me a linear equation for Cn. So I can find all the speed corrections, and the equations are linear. So even though I had non-invertible f prime of x naught, so the problem wasn't completely linear, the solvability conditions are linear, so I can find everything with linear operators and turn the crank as far as I want. And numerically, you can do this. And TFE is the way to do it, the way to get a nicely posed GN. So TFE being the transformations I discussed on the previous slides. But that's not the whole story, because sometimes this intersection is at an integer. And when is that? Well, I can write the phase speed, C naught. Here's C naught evaluated at k equals 1, and here's, or the phase speed at k equals 1, and here's the phase speed at k equals m. And if I asked you, fix the bond number, and tell me what m gives solutions where this speed is equal to this speed, that's a really complicated question. What is the relationship in m here? M appears inside of the tanh, appears here in some polynomial in m. That's asking you to find, well, in finite depth, the solutions to a transcendental equation over the integers. I can't do that. I can't solve a transcendental equation over the real numbers. And even if I go to infinite depth, where it effectively becomes polynomial in n, I can't solve polynomials over the integers. That's a complicated number theory problem. But what I can do is solve this equation for sigma. For the bond number appears simply in this. If you were to square both sides, you could collect the coefficients of sigma and divide, and just say m is an integer. Now I have a parameterization for the bond number in terms of the integers. So that's the way that we typically think about this. There's a countable set of bond numbers for which these waves exist. Not, here's a bond number, is there an m somewhere way out far that I tried to compute for which there's a ripple? That's a much harder problem. In fact, these ripples were first studied by Wilton. This is Wilton, J.R. Wilton. Wilton went to college here at Cambridge. Then he did a lectureship at Sheffield. Then he went to Manchester and worked under Lamb. And then he went to Adelaide, where he studied number theory for the rest of his life. And why did he do that? Because he got really interested in finding roots of polynomials or roots of elliptic curves over the integers because of this problem. And I have here, so that's Wilton. This is Wilton's application letter from Cambridge to Sheffield. So you can see here he was at Trinity. He was a 5th Wrangler at Trinity. So that means he was the 5th best graduate from his class. It's pretty good. Trinity's a good school. I think Stokes wasn't a 1st Wrangler either, so he's in good company. And so that's Wilton, and you can see it says recommended, so he got the job. So thanks to the people at Sheffield for sending me this. I kind of can't believe they're allowed to. They also sent me his letters of recommendation and his personal application letter. So it's really be careful in what you write in your cover letters, because 100 years later, somebody might have it and put it on a slide. All right, so okay, you can do everything that I'm going to talk about for the remainder of the talk in the context of the full water wave equations, but the finer details kind of get messy. And so to give you a feel for what you actually have to do, I'm going to present everything in a simple model that has all the same flavors. And the model is up here. So you could think of this as a weakly nonlinear version of the water wave equations, or you can think of it as a toy. It doesn't make any difference for our discussion today. So it's written in a traveling frame. I've even factored out the linear part. So L is going to be some pseudo-differential operator, which gives me the same type of phase speeds as I would get if I had used the full water wave equations. So if I solve the linear problem here when epsilon is 0, the phase speeds look like this, just like they did before. And I have the same kind of discussion where I draw a horizontal line and say, here's k equals 1. Is k equals 2 an intersection, or 3, or 4, or 5? Do they move at the same? Does the phase speed move at the same speed? Yes, Harvey.
Could you go back one slide?
Yes.
Well, I presume the integer thing comes in at that bottom line.
Yes.
Tell me why integers are important.
Because I'm on a periodic domain. So all the wave numbers are integers. If you went over the real line, these things would always be there, but it's not clear that they would have to interact. Right. Okay, so periodic domain, so now I'm on the integers, and I want to study the problem where the solution basically looks like e to the I x, so it's supported at k equals 1, and is supported also at some other frequency, m. And now, if I were to just solve the linear problem, well, linear problems allow superposition, so I could have e to the ix and any ratio of e to the mix, and I could add them together. It turns out the nonlinear problem, I cannot have any ratio of those two frequencies. I can only have special ratios. And so that means that somehow beta must be one of the unknowns of my problem. And if it is, well, probably it's just like the speed, where I don't get to fix it at the beginning, or even fix it at 0th order. I have to correct it at every order and amplitude. So that's how I'm going to have, when I have a two-dimensional kernel, two frequencies in the null space of the linear operator, I must somehow have two unknowns that get introduced to my series at every order so that I can impose two solvability conditions on these right-hand sides. And so that's what I'll do, is I'll say, okay, this is what I want the solution to roughly look like. Well, what will it actually look like? At every order in epsilon, I'll have U0, where I'll have homogeneous solutions that I'm free to add. And I'm going to add only some at this frequency, at IMX. So that is to say, I'll say my total solution U, how will I define its size? I'll define the size, the Fourier transform of e to the ix to be 1. And then I'll define the Fourier transform of the total solution at e to the imx to be beta. And beta is one of the things I'll solve for. So epsilon is effectively defined by this guy. And then this guy is defined by its ratio to that guy. Right, and then, so what that means is if I make U0 be e to the ix, all the later U1, U2, U3, they have no contribution to e to the ix. Whereas all the later U1, U2, U3, they do have some contribution to e to the imx. That's beta 1, beta 2, beta 3. Now I want to turn the crank. And I want to turn the crank almost the same way as before. So I'll plug in this whole series and I'll collect orders and I'll get the linearization applied to UN equals the stuff plugged into the right-hand side. So this is what I was trying to avoid writing in the Stokes or in the water wave problem. Because I would have not just a quadratic nonlinearity that would have this discrete convolution and the speed, which would have some discrete convolution, but I would have cubic nonlinearities and I'd have one in every single term, and I think it would be too much to look at on the board. So please bear with me that we have to at least write these convolutions once if we want to see what's going on. And so what do I have to do at every order? I have to find the things in the kernel of the adjoint. So here I've noticed there's a derivative on everything. So I'm going to just invert that. So there is actually another thing in the null space of the linear operator. It's constants, but I'm going to throw those away all the time. So I'm going to look for flat surfaces with zero mean. And then I'm going to find the remainder of the operator is self-adjoint, so I don't have to put a star. And I'll find the things in the kernel, and I'll impose orthogonality to those functions. And in the context we're thinking of now, there are two functions, e to the ix and e to the imx. So I got to make sure this whole right-hand side is orthogonal to, or has no support at those two frequencies. And that's going to give me two equations, and well, I'm going to have two unknowns. So I should be able to do this. And the question is, what's the flavor of the equations for those two unknowns? Are they linear, like they were for Stokes waves, so that I can blindly turn the crank? Or are they nonlinear? They could be in principle, two equations for two unknowns. I mean, there is nonlinearity in this problem, so there could be nonlinearity in my solvability conditions.
I'm sorry, Ben, what's P in the beta n minus?
I didn't say. So so it will be an equation for Cn at nth order. It will not be an equation for beta n. It'll be beta n minus something, some previous order coefficient of this beta. So that's exactly what we'll discuss in the next couple slides. What is P? And so the form of the equations for Cn and beta n depend on what is M. So if M is 2, I would call this a triad interaction. It's the classic Wilton's ripple. If M is 3, I would call it a quartet interaction, et cetera, et cetera. And depending on what interaction is going on, I'll get a different set of equations for Cn and beta n minus P. So P will actually be 1 if I have a triad and 2 if I have a quartet. And then I won't do it anymore because it gets too much.
So the higher the resonance, the longer you have to wait
to find
get your
beta.
corrections to the
That's
betas.
right. So we're going to see that exactly on the next couple slides. So I'm going to do the work, all the hard work for triads, and then I'm going to kind of believe that you all understand how it works now, and we're going to look quickly at quartets, and then we're going to say that's enough, because it just gets to be a lot more bookkeeping. So what am I actually doing? I solve the linear problem. I find the two modes in the linear solution. So here is the linear solution. U naught is e to the ix complex conjugate. The first correction, or beta naught times e to 2 ix. Right here I'm doing triad, so m is 2. And it's complex conjugate. And what do I need to impose? I need to impose that psi, which is also supported at these two same frequencies, is orthogonal to the nonlinearity at first order and the first speed correction. And the unknowns I'm trying to find are beta naught, which somehow appears in this nonlinearity and speed correction, and C1, which appears explicitly there. So what are the equations I'm going to get? Well, we're going to do this together. So what do I get from here? U naught squared. What's in U naught that's unknown? Beta naught. So there must be some beta naughts in here. And what part of the beta naughts do I want? I don't care if there's a beta naught at e to the 3ix, because that's not the thing I need to be orthogonal to. I only care if there's a beta naught contribution at e to the ix or e to the 2ix. So how from u naught squared can I get something at e to the ix? This is a tutorial, so we should interact. Take my inspiration from Thanos yesterday.
Exponential minus ix and exponential 2ix.
Yeah, so this guy interacting with that guy will give me an ix, right? I have u squared, so I'll have this one times that one. How many times will I have that? Well, so because I have u naught squared, so the first u naught can be this one, and the second one can be that one, or the reverse. So I'll get 2 copies of beta naught. So the red is color-coded, actually, so you could cheat now that you know that and figure out the next term. Similarly, so that's all the ways I can get e to the ix, so the typical triad interaction of this guy and that guy. And then, well, I must also be able to get more factors of e to the ix from this guy. So C1, how can I get C1ux, how can I get e to the ix out of that? It's the easiest possible way. There's e to the ix, and I can multiply it by C1. And I take a derivative, so there's really an I there, and there was an ik there, but they multiply both terms, and so I cancel them out, and I get this. Nice linear equation for C1 and beta naught. So I'm feeling really good, because I got linear equations, and that's what I know how to solve. But then I go and I do the k equals 2 case, and now what do I get from here? How can I get k equals 2? If here's u naught, and I plug into u naught squared, how can I get e to 2ix?
Only with ix squared.
Yeah, this guy squared only, right? And there's no longer this choice if I can take a ix from this one and a 2ix from the other one, because it's not the hybrid term of my product. So I get 1 copy of e to the ix. I actually plug it in here and get a e to the 2ix when I multiply them together and take a derivative. So I actually get a 2ik, but I'm also going to get a 2 from here, so I'm going to cancel the 2's and get a 1. So that's the 1 comes from the nonlinear term of e to the ix squared. And then I go over here, and now I have a C1. How can I get a 2ix? Well, I already have a 2ix, but I'm going to take a derivative. That's how I get the 2 that I canceled out. And I have a beta naught times C1. That's how I get this term. So color code still matches. I suppose it would have been nice if I had if I had switched the order of these terms so the blue could be on the left both times and the red could be on the right both times. But I think it's enough. So now we get these 2 equations. And what's the character of these equations? Are they linear or nonlinear? Are they transcendental? No, thank God. No, they're nonlinear, but it's not so bad. They're just quadratically nonlinear. And I can solve quadratics, luckily for me. So I can find the solutions here and how many they're going to be. How many solutions are there to a quadratic? 2. And it's actually the easiest possible quadratic. It's going to be one that's already factored for me. So it's not going to be something with a radical plus minus. It's going to be C1 equals plus or minus something, and beta naught equals plus or minus something. So I do that, and I find C1 and beta naught. And then I go to the next order. So we've had some practice. So we're going to do this one more time, and then I won't make you participate anymore. So now I go to the next order, order n, and then I get some much bigger equation. Lucky for me, most of the stuff in this equation is known at any order. So this is now at not just the next order, epsilon squared, but cubed, third, fourth, fifth, nth. Always looks like this. All this stuff involves terms I've already calculated completely. Same thing here. But then I have a couple terms which include the things which at order n are unknown. What's known right now? Right now I found C1 and beta is 0. So at order n, it's going to be a similar pattern. I'm going to have to find Cn and beta n minus 1. So that's what I have written here. The things I need to calculate this, I need to know, well, u naught has Cn multiplying it. Un minus 1 has these beta n's in them. Same thing here. U naught has, well, u naught is actually known at this level, but un minus 1 has beta n's in them. And what I can see right away, nice thing now, what are my unknowns again? So beta n minus 1, that comes in the un minus 1 and un minus 1, and Cn. So Cn is there. I no longer have products of my unknowns. Right? This guy has my unknowns in it, but u naught is known, and un minus 1 has my unknown. So that is not nonlinear in my unknowns. It's linear in my unknowns, which are here beta n. Same thing here. Cn is unknown, but u0 is now known. So that's linear in my unknowns. C1 is known, but un minus 1 has an unknown. So these three terms all have unknowns, but all the unknowns appear linearly. So I guess I'm not going to make you tell me what terms come from which again, but it's a very similar calculation. I have it color-coded again. Now we get a linear equation at every order instead of a nonlinear equation. So what do I need to do in order to formally compute these solutions? Well, I've made the right-hand side orthogonal to the null space of the kernel. So that means I can find the UNs if I can impose this at every order. And can I impose this? Well, that means I need to be able to solve this linear equation. Right? So I formally have solutions if this linear equation is invertible. And I've already computed C1 and beta naught explicitly, so you can check, and it doesn't take very long. It would be okay even if beta naught was 0, so long as C1 was not also 0. And then you can turn the crank to all orders and formally compute solutions. That's not to say I've computed anything. It may be that I can't sum the series, but I can at least write all the terms in the series. And if I don't have triads, then it gets more complicated. Why does it get more complicated? Well, at first order, I will have similar solvability conditions, but now I don't have the possibility of e to the 2ix plus e to the minus ix making e to the ix. So I lose one of the terms from this was the k equals 1 equation. And similarly, I lose one of the terms from the k equals 2 equation. And now I get two equations that just say C1 is 0. And beta naught, though, is arbitrary. So now I don't determine beta naught at the next order, and I got to go one order higher. Which means now I have to write the solution at U1, and it's going to have beta naughts in it, even beta naught squareds in it, and go to the next order, and now impose some solvability conditions that's going to determine stuff. And those solvability conditions are not just going to have triad interactions, they're going to have quartet interactions. So by quartets, I mean things like e to the ix, e to the 2ix, maybe another e to the minus ix. So 3 waves in it. So that's exactly what you get. And in fact, here m is 3 when you're doing quartets. I needed to not have m equals 2. So I can ask, what are the different ways I can get k equals 1? I can get k equals 1 by taking e to the 3ix, that's beta naught, is proportional to e to the 3ix. Beta naught bar is proportional to e to the minus 3ix, so 3 minus 3 cancels. And then times the e to the ix, that gives me a term like this as kind of the nonlinear Schrodinger nonlinearity term. I could also have the opposite. I could have I could have, what is the, oh yeah, this is the more complicated one actually. This is 3 minus 1 minus 1. This is 1 plus 1 minus 1. So we have all the different quartet interactions here. And what's the character of the equations now? So the unknowns are still beta naught and now C2. But what do I have to solve to find beta naught and C2? Maybe you call it a cubic. And maybe, I mean, there are cubic terms, but it's got moduluses inside of it, and it's a system of cubics. So anybody who's tried to teach their calculus students how to do like Lagrange multipliers recognizes that when you have a system of nonlinear equations and you try and solve them the wrong way, it gets more and more nonlinear. So to call this a cubic, I mean, it does have cubic nonlinearity, but it could really be as nonlinear as you want if you plug these in the wrong way. So I can no longer solve this explicitly, but it does have solutions. And if I find those solutions, then I can keep going, and the later orders have linear solvability just like they did before. A nice thing is that if I make m higher, most of the terms here still occur, because lots of the quartet interactions happen no matter what m is. So for example, this one and this one. So 3 minus 3 plus 1, 4 minus 4 plus 1, those still equal 1. 5 minus 5 plus 1. Same thing here, 1 minus 1 plus 1, that still exists. So the green terms, in fact, are the only two terms that are special to m equals 3. That's when 3 minus 1 equals 1. But 4 minus 1 equals 2. Same thing here. This is 1 plus 1 plus 1 equals 3. But 1 plus 1 plus 1 does not equal 4. You're learning some deep facts today. But if that's true, if I throw away the two green terms, I still have something that looks kind of like a cubic for beta naught and C. Right? So I'll still determine C2. And that means that the later solvability conditions will still be linear. And I'll still be able to turn the crank. I don't have to solve a cubic. At least all the time I don't have to solve a cubic. Sometimes so this is a cubic. The quartic or quintic or sextic, or whatever order polynomial you might think you would get if I make m bigger and bigger. Why did I say all the time, though? If you throw away this green term, these two equations look kind of similar, right? I have, if this one I could factor out a beta naught from, and then I might be tempted to choose C naught from this equation and choose beta naught equals 0 from this equation. And that's what will happen in general. But sometimes the coefficients will match and these two equations will be degenerate. So I'll be able to leave beta naught undetermined at this case. And by sometimes I mean almost never. So like doesn't happen in the water wave case, doesn't happen in this model. But it could happen in some model that you're interested in. It could be that there's some degeneracy that gamma 5 happens to equal gamma 3. That's what would need to happen. And similarly, gamma 4 would have to equal gamma 1. And if that happened, I wouldn't determine beta naught this order, and then I would get quartics and quintics and sextics, etc. if I wanted to do more complicated ripples.
Is there a way to count how many solutions you should be looking for?
Well, if I knew for some reason that beta naught was real, if I knew the phase, then I would have some algebraic system, and you'd be able to appeal to like the fundamental theorem of algebra and say how many roots there are. But here I cannot say. As soon as you put a modulus, I don't know a theorem that says how many solutions to these equations there are.
But
Yeah.
it's always a modulus squared. You could write it up in terms of real and imaginary parts, write it out as a couple of coupled polynomial equations, do resultants, eventually get down to a single polynomial.
So I mean, perhaps you could.
Yeah.
My experience is that it behaves as though, or that the betas are real. In which case, it's cubics, and then there's 3.
But even if it's not, I think there's ways to do it.
Yeah, I haven't done it. I'm aspiring to say I don't know as the answer to your question as often as possible, rather than make up an answer, which is much more tempting. Okay, so after you do this, you can find your beta naughts and C naughts, and you can write all the coefficients in your series, all the UNs, all the CNs, the beta n's are hidden inside of here, and then you could sum them. And now, if they're summable, then you get the solution, and it might look like this. So here's an example of what a triad looks like. You can see it basically looks like it has 2 frequencies involved, the fundamental one of k equals 1, and then something that's twice as oscillatory. And then if I do a quartet, then it should have k equals 1 and k equals 3, and so it's got a period of 2 pi, but then it also has a frequency 3 thing. And well, there's 2 different triads that are basically different by a sign, but there's 3 different quartets. So here are 2 examples of how the quartets look differently. And different values of epsilon are chosen here where the series is summable. So it's labeled at the top, epsilon equals 1.5, 0.125, 0.06. What you'll notice is epsilon is not the height of the wave. Not even close, actually. Epsilon, I defined here to be the coefficient of e to the I x. Right? So if the coefficient of e to the I x is 1, and I add its complex conjugate, the leading order thing is like 2 epsilon cosine. So if epsilon is 0.15, twice 0.15 is 0.3, and that's a reasonable estimate for how big the wave will be. It's actually not 0.3, right? See, this kind of tells you how nonlinear it is. So there's 0.3 and it goes up to 0.45 or something like that. So that epsilon doesn't actually quite tell you how nonlinear, kind of epsilon squared tells you how nonlinear.
So
Yeah.
I had a comment. So yesterday during Tang's talk, we had a question about could there be non-symmetric periodic capillary gravity waves? And so this was the mechanism I could imagine for producing such things. So you get at the linear order, you get the e to the I x, which is nice and symmetric. Then you get plus beta naught times something else, e to the I mx. But you can't pick just any old beta naught. If
That's
you
right.
pick any old beta naught, then maybe you could get something which was not symmetric. Has it been your experience that when you turn the crank, I mean, you can pick different m's, and then the different m's give you different betas.
Right,
beta
so
naughts.
I guess
Have
what
you
you're
ever
saying
seen
is,
something-
can I have complex beta naught? If beta naught could be pure imaginary, then I would have asymmetric waves, because it'd be like adding cosine with sine. But as you see here, the beta naughts seem to always be real. So then it's like adding cosine with cosine, and you don't get something asymmetric. I don't know if that's intrinsic to my model or to the water waves. My experience is that the water waves don't take odd solutions. So even if you do Stokes waves and you plug in e to the I x, the phase is free, right? So I could plug in cosine of x to start, or I could plug in sine of x to start. If I turn the crank to the next order, you always get cosine. The next order phase is an even function, is not an odd function, which is why waves look like, water waves at first approximation look like this, right? So I can shift this and make it even or odd. But the next order of the approximation, depending on how much surface tension or gravity you have, either look like this with flatter troughs, or look like this with flatter crests, and repeat over and over again. But although this could be even or odd depending on how I shift it, this cannot be odd no matter how I shift it. And same thing there. So that is kind of my feeling about why this is.
I think there's a theorem, if you have no surface tension, I think it's Walter's theorem, that says if you have no surface tension, then your wave has to be symmetric
So actually,
in 2D.
so I did some reading
Solitary
yesterday.
waves.
Yeah, but for periodic waves.
Periodic wave is not symmetric.
Right, so.
Pure gravity.
Yeah, so we looked at the paper that you shared.
But the capillary gravity wave, periodic waves, may be non-symmetric.
Even pure gravity waves.
Even pure gravity is Zofree has a computation.
So he shared a paper with us, and then we looked, and there's some pictures in there, and they're, believe me, very asymmetric.
But not, but I bet they're not odd.
Is this a Furia paper from '87?
No, it's actually not. It's a
No,
more recent
no.
paper that.
For
we
pure
posted.
gravity waves, Zofree's paper in 1987 shows there's non-symmetric periodic wave. Pure
Right.
gravity waves.
Yes.
Right, but the other paper that you showed, the
That's right.
86 paper, has some very nice pictures that.
For non-symmetric capillary gravity waves.
Yeah.
Oh.
John,
In
Are they
terms of
odd?
In terms of odd, it's, I mean, you just look at the water wave equation, odd is not possible.
Yeah.
Odd is not.
All
That-
is not
that's what I thought.
Right.
I'm sorry, but the question is that the wave, the solution is invariant under the shift of variables. Therefore, if you have solution of nonlinear problem, then time derivative of this solution will be eigenfunction of the linear problem. Therefore, linear problem in any case have zero-like eigenvalues. If you take gravity waves, you can split on the odd, on the even spaces. On the even spaces, spaces of 0 would be the first eigenvalue in any case. Therefore, it is a block for bifurcation for even non-symmetric waves. But for odd. But if for in even space, eigenvalues come through 0 into negative parts and generate bifurcation, secondary bifurcation, third kind bifurcation, something. Therefore, the question about non-symmetric waves, it is very delicate questions. But however, in stratified liquid, you know that like in type solutions, they exist and they are not symmetric. It is question very delicate and needs theoretical investigation.
Good. All right. So, right. So then the question that I guess still remains for us in this discussion is, so I have some solutions that I summed. How big can epsilon be? Or that's what remains is I'm formally summing them, and I'm summing some of them and seeing if I get data out. That doesn't. I mean, but I sum them to find an m. What if I kept going and added more m? Is this actually something that converges, or is it just the sum of some terms? So that's something you could investigate numerically, or you could prove it by hand. So numerically, how would you go about investigating that? Well, you have formula for these UNs. So you might say, how fast do they grow? Or the CNs, how fast do they grow? And you might do something like, so this, in my toy model, L was the dispersion relation, and I can pick lots of different dispersion relations. Depending on which one, I'll get different growth rates. So this is fifth order KdV, and this is some other models that look more like gravity capillary waves in deep water. So with the gravity capillary dispersion relation is one of them. I think another one is the flexural gravity capillary wave dispersion relation. You can pick whatever you want and see, well, how fast do these things grow? And the slope of the line doesn't actually matter, just the fact that it's a line. So this is a log-log plot, so if it's a line, that means the coefficients grow like d to the n. And if they grow like d to the n, then I can pick epsilon smaller than d, and the thing is summable for some finite radius of epsilon. So the slope here tells me how big epsilon can be. So that would be one thing to do. Another thing to do would be, yeah, Olga?
So how do you actually compute all of those coefficients? Do you do them numerically, or do you?
Yeah, numerically. So that's what this procedure is. I find all the UNs and CNs, and I basically do, in this problem, I would do just symbolic algebra. Right? Here, everything you can do explicitly in the weakly nonlinear model, because there's no vertical dimension that I have to discretize. In the water wave problem, I have to discretize the vertical, so I have to do some like elliptic solver, like ODE solver for the vertical. But that's the only thing I have to do that's numerical to find the UNs. And then I have the formula for them, and I can take their norms, or I can just look at, it's easier to look at C. C is a scalar valued thing. So in terms of C here, this is C, I can plot, I guess the black curve is the Taylor sum So it's exactly what I have written here, but first course in numerical analysis, you might say, oh, well, Taylor sums are always going to have, a finite Taylor sum is always going to diverge, but I might instead use pad A and analytically continue these things and see how far they actually go. So the black one is a Taylor sum of the speed, the red one is a pad A interpolant to the speed, the diagonal pad A interpolant, and the blue triangles are what you would get if you just used Newton's method and continued. So what I'll call the real answer. And you can see that with pad A, I could extend these things and follow it for as long as I had the patience to follow the branches with Newton's method. It's interesting, Philippe brought up a good question. If I wanted to look at the profiles here, I don't know what I would do. I don't know what it means to pad A interpolate functions instead of scalars.
You can do it pointwise.
At every point, I could pad A
Every
interpolate.
point, or you can do it at every Fourier coefficient,
Yeah.
and then sum them up.
I would like to just use the same pad A interpolant from the speed and plug in the function.
Sadly, no.
Yeah. Right, so that's what you can do. And then, of course, you might also be interested in a proof. So Dave has a proof for the water waves for the Stokes case. We're working on something for Wilton ripples. You can also do a very similar thing for the spectrum if you want to know whether the eigenvalues are analytic in such an expansion and what's involved. So you do strong induction and what are the ingredients. I want to prove something like the norm of un in some space is less than d to the n. It turns out you need not d to the n, but d to the n over n to the p. No matter what p is, you get effectively the same prediction for your radius of convergence. It's just dictated by d. But what must be true? Well, you need to pick S big enough so that HS is an algebra. Because you have nonlinear terms, you're going to take the norm of a product, and you want that product to be in the space still. You need to be able to invert the linear operator and still stay in the space you're taking the norm in. So you need some elliptic estimate. So there's one by Beal, or there's a couple in Dave's papers you can read. It's going to vary by your problem, of course. If you do this weakly nonlinear problem, you need a different estimate than if you do the water wave problem. And then we're doing induction, so at some point I have to do the inductive step. So that's where I need this n to the peak. I need to pick p so that this sum is bounded for all n. So this is not a sum from 0 to infinity, it's a sum from 0 to n minus 1. And what does it look like? It's got n on the top, so n is going to infinity, and it's got n to the p over something else that's less than n to the p in the bottom. And you can bound this series from p bigger than 2. And now what the value of the maximum of this series for all n is the thing that's going to come in and help you pick C and help you pick D. So the maximum of the series is going to set the maximum of the series times CD will be fixed by one base case, and then the other value of C or D will be fixed by the other base case. And then you could, in principle, analytically give an estimate for D that predicts your radius of convergence. Even in toy problems, I haven't been able to make that bound sharp. So if you did this just for a cubic, you can get values of C and D and know that you're analytic for an interval, but you don't actually get the interval where the roots of the cubic are analytic. You get a lower bound for the roots or the area where the things are analytic. So unfortunately, I wouldn't advocate this as a method for showing to what radius your series converges, or as a numerical method, find C and D. I would advocate using the numerics to find the radius and using this to show that your numerics make sense. But Dave will talk a lot more about that tomorrow, so if you're angry that I didn't explain to you what it means for HS to be an algebra well, you'll have a second opportunity. And that's everything I have to say. So we have 5 minutes for you to ask me about anything you want. Thank you very much.
Any more questions?
Did you, along with Higgins, I don't know how long ago that was, in 78 or so.
Yeah, he has a paper like some modification of the coefficients for Stokes waves. Is that the one you're talking about?
Yeah, it was, well, he was doing an infinitely long expansion with, I think he was doing this conformal mapping, I think it was just for 2D. And then he plotted things like, the energy as function of the phase speed or the steepness.
Yeah.
So did you compare your results with his?
I have not.
Up to the 6 digits?
I mean, you could.
Yeah, it's his 1975 paper where he looks at integral properties of Stokes.
Yeah.
Yeah, 1975.
Yeah, that's around that period.
There's also the paper by Coakley.
Yeah. It would be interesting to compare it, because that's the first time it was done, right? Isn't it? Where it was done accurately.
Anybody else? All right, so I think we have a break for coffee before the next tutorial, so you feel free to ask me questions during coffee.